Humans have always wanted to understand how the world works. Philosophers like Aristotle believed that the world was made of four elements: water, earth, fire, and air, like the intro to Avatar The Last Airbender. In the 19th century, Dmitry Mendeleev proposed that the world was made of elements in the periodic table. Though he didn't actually create the table that we use today, he inspired the idea. Eventually, scientists found that the atom was composed of subatomic particles: the proton, the neutron, and the electron. Thanks to the hard work of J.J. Thomson, Ernest Rutherford, and James Chadwick, we were so much closer to discovering the secrets of the universe. The question still remains: what composes these subatomic particles? String theory, sometimes called the theory of everything, seeks to provide a complete model for many unexplained things in the universe, like the composition of these subatomic particles. Within this theory, all particles are described as one-dimensional strings, hence the name. However, to understand string theory, we first have to understand the Standard Model.
The Standard Model describes the fundamental particles which make up our universe. These particles can be categorized as composite or elementary. Elementary particles can be divided into fermions, which are associated with matter, and bosons, which are force-carrying particles. Fermions can further be divided into quarks and leptons. Quarks are heavy particles which can be classified as up, down, top, bottom, charm, and strange. Meanwhile, leptons can be divided into electrons, muons, tau particles, electron neutrinos, muon neutrinos, and tau neutrinos. Within the set of bosons, the photon, gluon, W, and Z bosons are classified as gauge bosons. There is also the recently discovered Higgs boson. Composite particles, also known as hadrons, are made of multiple elementary particles. Baryons, such as protons and neutrons, are composed of three quarks held together by gluons. The proton, for example, has two up quarks and a down quark. Mesons, meanwhile, are hadrons with two quarks. For example, the pion is made with an up and a down quark, one being antimatter and the other being normal matter. In the Standard Model, there are four fundamental forces: the gravitational force, the electromagnetic force, the strong force, and the weak force. These forces are caused by the exchange of bosons between particles. One weakness of the Standard Model is that it does not describe why particles have the properties that they do and what they are made of. It also does not explain what causes gravity. String theory hopes to address these problems.
Originally, string theory only described bosons and was called bosonic string theory. Modern string theory is known as superstring theory and describes both bosons and fermions. In superstring theory, essentially, all the different elementary particles we know of are simply different manifestations of strings. Everything is made of strings. How nice, right? The lengths of these strings are so small that they cannot be distinguished from points, observationally.
Essential to string theory is the idea of higher dimensions beyond the normal three which are observable. These extra dimensions are considered compactified. Although these may appear to be one-dimensional lines when seen from a larger scale, when seen on a much smaller scale, it can be seen that they have a small circular dimension. How these strings wrap around these dimensions and vibrate determines their properties, such as mass and charge. Modern mathematical models show that there must be 6 compactified dimensions for string theory to work. Since there is more than one compactified dimension, the compact dimensions do not take the shape of cylinders. Rather, they form a 6-dimensional space known as a Calabi-Yau manifold. Although too small for any large matter to interact with, individual strings are constantly interacting with these small dimensions. The 3 space dimensions, along with time in the compactified dimensions, give string theory a total of 10 dimensions.
Supersymmetry, the unifying center of superstring theory, links the fermions, which are matter particles, and bosons, which are force particles. The idea of supersymmetry was formulated to combat the crisis that physicists faced when trying to calculate the mass of the Higgs boson. The Higgs boson was a recently discovered particle whose interaction with other particles gave them mass. However, the original theory predicted all particles to have no mass. Thus, supersymmetry, which acknowledges the Higgs boson, gives the other particles mass, solving the universe with no mass issue. In supersymmetry, every fermion and boson has a partner of the other type. For example, the electron, a fermion, would have a boson counterpart called the selectron. Supersymmetry predicts a partner particle for all parts of our current Standard Model. Some have theorized that these partner particles make up dark matter, the invisible, undetectable substance that makes up most of the mass in our universe. String theory also requires the existence of a particle called the graviton. The graviton would be the force-carrying boson for gravity. However, the graviton is not included in the standard model. This particle could help explain the existence of dark matter as well. Unfortunately, the existence of the graviton has not yet been proven.
There are 6 different models for how strings work, varying on things such as whether the strings are closed, connecting to themselves in a circle, or are open. These models are unified by M-theory, which suggests that they are all aspects of the same theory. M-theory also introduces the idea of branes, strings which are two-dimensional rather than one-dimensional. As a result of branes, an extra dimension is required, bringing the total up to 11.
Currently, no actual evidence for string theory has been found, so neither extra dimensions nor strings have ever been observed. In addition, supersymmetric partner particles have not been found as well. However, scientists are trying to collide particles to see if they can produce supersymmetric particles or send them into higher dimensions. Although we have much to learn about string theory and have yet to prove it, it has great potential to further our understanding of the universe.